Okay, so today we're going to be talking all about logic gates. Logic gates are quite a unique part for your CIE course. They do appear on other exam boards, but probably quite a lot more detail really on the CIE course. So, by the end of this lesson, you're going to be able to identify and describe some logic gates, and we're going to look at how to identify the output of multiple logic gates as well. So let's just start with the idea of why we use logic gates. Let's think about using relays first to turn on a light if it is simultaneously cold and dark. So hopefully when you see cold, you think, okay, I'm going to need a thermistor. And if it is dark, I'm going to need an LDR. So when we're wanting to use these as sensing circuits, we're wanting to make decisions, we're going to need some potential dividers. Now the easiest way to do this is I'm going to introduce a new type of notation. Sometimes in physics what we do is we draw terminals. So I'm drawing here two circles, and I'm just going to say that this terminal up here will be at plus 5 volts, and this terminal down here will be at 0 volts. Now what you can actually do in your head is you can imagine that these 2 points, they are connected by a battery between the two of them. That's a terrible colour to use. Let's change to a better colour. Okay, you can imagine they're connected by a battery between the two. But we often don't actually draw that battery in. Instead we work without that battery. So we just leave them looking like this. Now, the first thing I want is something that will turn on when it is cold. So for something that will turn on when it's cold, I'm going to need a potential divider with a thermistor in it. So there's my thermistor. And let's make this something that you can control. So I'm also going to include a variable resistor here. Remember, that's a symbol for a variable resistor. Now, when I look at this circuit, I need to think what will happen as this gets cold. So I'm interested in the temperature, and I'm interested in the resistance of the thermistor, and I'm interested in the voltage across the thermistor. So, when the temperature goes up, the resistance across the thermistor will drop. Because the resistance of the thermistor drops, the voltage across it will drop. When the temperature gets cold, the resistance goes up, so the voltage goes up. Now, I want something that will turn on when the thermistor is cold. So what I need to do is take my voltage out from my thermistor. Now if this is at 5 volts up here, that means that I'm going to want to measure a voltage across this thermistor here. So in other words, I want a big drop, so I'm going to measure my output here. I also want something that will switch on when the light level is low. So for that, I'm going to need an LDR. And again, just so it's configurable, I will also need a variable resistor. Now for this one, I can say when the light level, again, how will that affect the resistance of the LDR, and how will that affect the voltage of the LDR? Well, when the light level is high, then the resistance will be low, and the voltage will be low. When the light level is low, the resistance of the LDR will be high, and its voltage will be high. So I also want to take the output voltage from the LDR as well. So now I have these two separate devices where I have voltage from my thermistor, and I have a voltage from my LDR. And now I want to use a relay so that it will turn on a lamp. So let's put a lamp in here. I want that lamp to turn on when it is simultaneously, I have a high voltage here and I have a high voltage here. Now there's actually a quite easy way of doing that. What I can do is I can connect both of these to relays, and then I can put these relays in series, like that. Because now this lamp will only switch on when both relays are closed, and both relays will only be closed when both of these have high voltages. Now, you may have noticed in the previous diagram when I was talking about that, I was talking about voltage being high or voltage being low. And this is the idea of digital signals. So digital signals, we view them as just digital signals we view as just two possible values. We view them as either a 0 or a 1. So what we often call is a high and a low. Now, for a lot of things, this high is 3 volts and low is 0 volts. Some devices use 1.5 volts for high and 0 for low. Some use completely different voltages. But the idea is any time the voltage is high, we call that a 1. Anytime the voltage is low, we call that a 0. And that's different to analog signals. So analog signals can take any value. But what we could do is we can convert things from analog to digital. So if we say that anything above this red dotted line would count as a 1, then my digital signal would look like this. Yeah, only becomes a 1, whoops, that's gone too far, only becomes a 1 when my voltage goes above a certain point. And there's lots of advantages to digital signals. You can clean them up really easily, so that's why if you watch Astro or digital TV, you never really get, you either get a perfect signal or no signal at all, because you either have a voltage that's high and low, and you can very easily say if this signal gets a little bit messy, it might turn into this. But you can still really easily see what's high and what's low, and because a computer only cares about high or low, it's really easy to recover signals. That doesn't come up a lot on CIE, but it's worth just knowing about. Okay, so let's think about a logic gate. What a logic gate is something that can be connected to a sensing circuit, and they will give you different types of outputs. So we represent them as a truth table. So we have one side that shows what we're putting in, and an X side which shows what will come out of that logic gate. And there are 4 types of logic gates that you need to know for CIE. There are other types of logic gates as well, but you don't need to know them for CIE IGCSE. So the first type of logic we're going to look at is a NOT gate. So the truth table for NOT gates shows us that I can put in either a 0 or a 1. So this would be a low voltage, the 0, the 1 would be a high voltage. And what we find with a logic gate, with a NOT gate, is that if I put in a 1 to a NOT gate, the NOT gate will produce a 0 at the other end. In other words, whatever goes into a NOT gate, it gives me the opposite. So if high voltage goes into a NOT gate, the NOT gate will give me out a low voltage. If I put in a low voltage, I will get out a high voltage. So it swaps it to the opposite. An AND gate has a slightly more complicated truth table because an AND gate has 2 inputs, and we usually label them A and B. So here in my truth table, I've put in all the possible combinations of A and B. And what you'll see with an AND gate is that will give false, so it will give a low voltage or a 0 voltage in all cases except for where B and A are true. That's when it will give out a true itself. Now a NAND gate is quite a clever one. What a NAND gate actually is an AND gate followed by a NOT gate. Now if you look at the symbol here, can you see I've got this circle on the end of a NOT gate, and I put that same circle at the end of a NOT AND gate or a NAND gate. So what it effectively does is it gives you the opposite output of an AND gate. So it will give you a 1 here, a 1 here, a 1 here, and a 0 here. In other words, this one will always give you a high voltage or a 1 in every case except for when A and B are both true, because it's going to take the opposite of an AND gate. For an OR gate, it will give you out a 1 or a true whenever either A or, hence the name, or B are true. So for when they're both 0, it will give a false. But when A or B, or in fact both of them are true, it will give a true output as well. There is one more just to think about. I wonder if you can guess. If I draw a gate like this, so this is an OR gate, and then I've put a circle on the end. What type of gate do you think this could be? Well, this will be a AND or a NOT OR gate. And if we think about its truth table, so I'll have A, B, and its output. Let's label those as well, A, B, and output. Well, this one again, it'll just be the opposite of a normal OR gate. So I can have 0, 0, 0, 1, 1, 0, 1, 1. Its output then will be 1, 0, 0, 0. It will be the opposite of an OR gate. That one shouldn't come up on CIE, but they might use it just to throw in a spanner in the works. So this is where we get into the really cool thing. Sometimes you might be asked to combine logic gates. So here I've got an AND gate followed by an OR gate, and I'm going to have my output here. So a classic exam question will be to make a truth table for this logic gate. So to do this, what we need to do is write down our possible inputs, and then we're going to want to get out my final output. So in the exam, they'll probably do this part for you, because counting in binary is really boring and a little bit difficult, especially when you're trying to do it on video and not make a mistake. Yep, there we go, that's all the possible truth tables. Now, what I'm going to do is I'm actually going to create another point here called point D, because A and B together, they're going to give me one output, so it's an intermediate point. Sometimes you'll see it referred to that in an exam. I'll label that as an intermediate point. In other words, it's in the middle of something else. So, if A and B are both 0, D will be 0. Then I can say, well, going into the OR gate, I've got D and C. In that case, neither of them is high, so X will also be 0. If A and B are both 0 again, D will still be 0. But now for my X point, X has D and C going into it. So D is 0, but C is 1, and this is an OR gate, so it will give true if either is true, so X will be 1. For this one, when B is 1 and A is 0, point D, this is an AND gate, so it will still be 0. And now I can just look back to my previous answer. I know when C is 0 and D is 0, X will be 0. A and B are still 0 and 1, so D will still be 0. But now C is 1, D is 0. I've already worked that out. I know X will be 1. This one again will be 0. I've now got 0 and 0, so X will be 0. 0 and 0, so D will be 0. But now I've got C and C is true, D is false, so X will be true. This is where it starts to get interesting. A and B are now both true, so D will be true, because this is an AND gate. This is our first time D's been true, because it's the first time that both A and B have been true. I've now got, over here, going into my OR gate, D is a 1, C is a 0. It's an OR gate, though, so provided one of those is true, the OR gate will give out true, so this will be a 1. And then finally, an AND gate, so A and B both being 1, D will be 1. And now OR gates, either or, it can be both, so X will be 1 as well. Usually in the exam, they won't make you do the full table, they'll just get you to fill in a couple of blanks here, but this is a general pattern that you'd use. Okay, so let's go back to our original idea. We wanted a system that will switch on a heater when it is cold and dark. So now what we can do is we can replace our original diagram with one that uses logic gates. So here's my thermistor. Here's my variable resistor. So this is the first one. And what I'm going to do is I'm going to take the output of this and I'm going to label it A. Then I'm going to have my LDR. So this one will respond to the light changes. And again, I'll put in a variable resistor so I can configure this and control it. And if I want to, say, change the amount of light that's needed, I can do that. And I'm going to call this B. Now I want it to switch on if it is cold and dark. So what I can do is take these outputs and I can put them into a logic gate. And then this would be my output. So I could then connect this, say, to a relay to turn on a light or something like this. What about if I change this and said to make cold or dark? Well, in that case, it becomes really simple. All I need to do is swap this logic gate for an AND gate. Sorry, an OR gate. So that's a symbol for an OR gate. And now this will switch on when either of these is true. What about if I wanted to change it to when it's hot or dark? Well, again, what I can do now is at the moment, this one will give me true when the thermistor is cold, but the clever thing I can do is, along this input, I can add a logic gate. So I can take my output and then I can put it through a NOT gate before it gets to my OR gate. So now this one will be true when hot. So now this input A will go true when it is hot. That's all I've got for you this lesson. It's a lot to work on, so don't worry if you're a little bit intimidated by it right now. Just do some practice at it and you're going to be absolutely fine.